In this video, looking at spontaneous collapse theories, we will be looking at how this works with multiple particles. I've already hinted at how this works in previous videos, but we're going to look at it more explicitly in this one. So the generalization of the theory to many particle systems is just that each individual particle suffers the spontaneous localizations that we discussed in the previous video. The difference is that now there can be entanglement. But first, let us consider an unentangled two-particle system. At the moment t minus, just before the spontaneous localization, the system has this quantum state here, where this is our particle 2 and this is our particle 1. It is irreducibly random which particle undergoes spontaneous localization, but if we say that particle 2 suffers a localization at t naught here, then at t plus just after that we have this right here. So this is our Gaussian right here. This is our wave function just before the localization, and this is the normalization factor. So the normalization factor is such that the square of it is equal to this, so it's just the integral of the Gaussian times the wave function right here. Likewise, the probability density for the localization to be centered at point R is equal to the square of this normalization factor. So plugging in these things into our equation, so our wave function being these two particles here, and plugging it into this, we end up getting this right here. So our first particle right here is unchanged, and the second particle right here has the Gaussian and the normalization. And what that means is that the quantum state has no entanglement. Each individual spontaneous localization only affects the particular particle hit by the localization. Here we're talking about particle 2, resulting in an unentangled product state with particle 1 unaffected. But if there is entanglement, then we can consider a pair of entangled particles, where either both are located at x equals plus a, or both located at x equals negative a. So at time t negative, just before one of the particles undergoes a spontaneous localization, the two-particle wave function is this. So we can have them either at positive a or here at negative a. If the wave function of one of the particles suffers a spontaneous localization, such as particle 2, then we have this right here. So this is our Gaussian, this is our wave function just before the localization, and the normalization factor. So R is random with a probability distribution here, so the place in where it is actually going to localize is going to be random, but with this probability distribution here. So this is given by our Gaussian and by our wave function here. So just like we saw in the previous video, the wave function sort of tells you where this thing can actually localize to, and then the Gaussian will sort of multiply by that wave function to actually localize it. So this will have a large probability in a sigma-sized area around both r equals plus a and r equals negative a for both particles. If, say, the localization occurs at r equals plus a, then the two-particle wave function after the localization will be this. So this is our two-particle system right here, multiplied by our Gaussian. So we then put the Gaussian right here, and then this is our two-particle wave function. We do a little bit of a math here, and what we end up with is this, where the Gaussian multiplies here, and the Gaussian multiplies here. So I labeled it in green and red. So the green Gaussian here is large, and the red one is small if the separation is greater than sigma, which means that both particles will then show up at r equals plus a. And so we can think about it this way. So right here on the left, we have the configuration space map for the two-particle wave function for the two particles in a superposition of both particles on the left and both particles on the right. The right up here graph is the same map after a single spontaneous localization. Despite nominally acting on just one of the two particles, the spontaneous localization gives rise to a wave function which has both particles localized together. And so that's because of the entanglement. We end up with one of them suffering the localization. Entanglement makes it so that the other one also suffers the localization, and they both end up in the same place. But it does not actually matter that it was particle 2 that suffered the localization, because the same thing would have occurred if it had been particle 1 that localized at x equals plus a. Similarly, if either particle had spontaneously located at x equals negative a, then both would have suffered the localization. Now, if we had some macroscopic collection of particles, so say on the order of n equals 10 to the 23 particles that are all entangled, we could have an initial state t minus. And so that looks like this right here. So these are all the particles right here in the one state, and these are all the particles in the other state. This means that if any one of the n equals 10 to the 23 particles suffers a spontaneous localization, the entire set of entangled particles will localize. And so there is a 50% chance of it being at plus a and a 50% chance of it being at negative a. We saw in an earlier video that with a single particle, we need to wait for a long time, about 300 million years per particle. So if 2 particles, then we have to divide this by 2, so it's 300 million years divided by 2 particles, which gives us 150 million years per particle. And so with n equals 10 to the 23, we end up getting 3 times 10 to the negative 15 years per particle, and that is about 30 nanoseconds per particle. So in other words, there will be a localization about once every 30 nanoseconds, which is millions to billions of localizations per second for macroscopic systems. So John Stuart Bell said of this, quite generally, any embarrassing macroscopic ambiguity in the usual theory is only momentary in GRW theory. The cat is not both dead and alive for more than a split second. We can think about this as a quantum measurement process with a single particle in a box beginning in a superposition of several different energy eigenstates. The Schrödinger equation says that we have wave function of the particle pointer system at time t as this right here, where x is the position of the particle and y is the position of our pointer. So the psi I here are the energy eigenfunctions with energy eigenvalues of E sub I, and this phi sub naught is a narrow Gaussian wave packet representing the position of the center of mass of the n equals 10 to the 23 particles composing the pointer. So we're saying the pointer is a macroscopic collection of particles on the order of 10 to the 23. So the pointer remains in its initial state, suffering millions to billions of localizations every second. Upon interacting with the particle in a box, the pointer enters a superposition of, say, y1, y2, and y3, but only for about 30 nanoseconds before one of the particles collapses, causing all n equals 10 to the 23 particles, which would include our particle in a box, to collapse to, say, y2. And so that looks like this. So we have this superposition over here, and then it ends up collapsing into y2 right here. So the evolution of the wave function in the schematic two-dimensional configuration space, as soon as the individual terms in the superposition, which are separating along the y direction in configuration space, have separation of order sigma, the superposition collapses to just one term, randomly selected from all the possibilities, with probability of this c squared here. Thus, before there could be any time for anybody to notice or worry about a troubling macroscopic superposition, the overall wave function describes the pointer as having a well-defined center of mass position. Here we can arbitrarily say it's at y2, and the particle in a box as having the correct associated energy. And so notice that although the particle is localized in position space, the particle in a box ends up in a state of definite energy corresponding to the definite position of the pointer. This shows why we only need to talk about spontaneous collapses in position space. What this tells us then is that the collapse observed upon measurement of a quantum system occurs because, within a tiny fraction of a second upon interacting with the measurement apparatus and becoming entangled with it, the entire system, the particle plus measuring apparatus, suffers a spontaneous localization that would have occurred whether or not an observer was there watching the measurement apparatus. Which means that we don't get these weird things about having to talk about measurements and observers. We don't have to think about what a measurement actually is. We don't have to think about what an observer actually is. These spontaneous collapses are happening all the time, and so when our particle in a box becomes entangled with our measurement apparatus, then it will also spontaneously collapse. Thus, it only appears like the particle collapses due to some mysterious process we call a measurement, but in fact collapses due to the spontaneous localization of the entire entangled system of n equals 10 to the 23 particles. This would have occurred whether or not we called the large entangled system a measurement device. And so that is how this is going to solve the measurement problem. But anyway, that was everything I wanted to talk about in this video. I hope you found that interesting, and I will see you in the next one.